Hey guys, so in this video I'm going to be going through the next section in FreqAI, which is parameter table, which I think it's pretty easy, but let's see. All right, now what we are seeing here is that these parameters. All right, so let me go ahead and show you guys. Okay, now well, the first thing we want to do is that we want to enable our FreqAI. All right, so here the table below will list all configuration parameters available for FreqAI. Some of the parameters are exemplified in config, this example here, and mandatory parameters are marked as required and have to be set in one of the suggested ways. Okay, so let's go ahead. And let's see what we have here. Okay, so here general configuration parameters. All right, so now FreqAI, right? So we wanna, it is required, so the parent dictionary containing all the parameters for controlling FreqAI. Okay, train period days will be set FreqAI enable true. Train period days is set to 15 days here. So this is the number of days to use for training data with the width of the sliding window. So this is width of the sliding window. All right, now let's move on. Backtesting periods. So backtesting period days is set to 7 days here. So the number of days to inference from the trained model before sliding the train period days window defined above, and retraining the model during backtesting. More info here. This can be a fractional days, but beware that the provided time range will be divided by this number to yield the number of training necessary to complete the backtest. So this is for backtesting, right? And then 15 days is for train period days. So it's saying that for the number of days to inference from the trained model before sliding, okay, the train period days, okay, windows defined above. Okay, so it is basically, and also it's saying that it's retraining the model during backtesting. So yeah, right now what we have here is identifier, a unique ID for the current model. If the model are saved to disk, the identifier allows for reloading a specific pre-trained model. Okay, is it good? Okay, let's try. Now we have live retrain hours, which is frequency of retraining during try and live runs. Okay, so we have live retrain hours is set to 0 here. So it is saying frequency of retraining during try and live runs. So we can set it to 1 hours. Basically, it's saying that like after every 1 hours I want to retrain my model, right? Now expiration hours says that it avoid making predictions if a model is more than expiration hours old. So if the model is 2 hours old, we don't want prediction from that model. We want to retrain it and get the prediction. Okay, and yeah, see prediction. All right, we don't want to use the old model, so here we can set that using expiration hours. Here it hasn't defined here, so let's just quickly go and add it. Okay, we want to add live retrain hours to 1, and we want to add our expiration hours to 2. Okay, now let's go ahead and see what we have here. Whether we want to purge old models or not, which is delete obsolete models. So default is false, meaning all historic models remain on disk, right? So we can basically set it to true because we don't want to like save very old model. So here, meaning expiration hours is to delete that model, retrain it, and then save it, and then if the 2 hours has passed, delete it, so that it basically in a more optimized way to save disk space as well, and performance too. So here we have save backtest models, which actually saves models to disk when running backtest. Okay, so here we can see if there is save backtest model. So here it is not. I think we can add it later though. Yeah. Backtesting operates most efficiently by saving the prediction data and reusing them directly for subsequent runs. When you wish to tune entry exit parameters, okay, then you want to do save backtest models, right? Now saving backtesting models to disk also allows to use the same model files for starting a dry or live instance with the same model identifier. Okay, so it is quite useful, I think. So let's go ahead and add it. Now what we have here is that save, wanna save our backtest model, set to. Now fit live predictions candles. So it is number of historical candles to use for computing target levels statistics from prediction data instead of from the training data set, right? So we had actually looked into this, and here it is, fit live predictions. Okay, actually it was in the example. Okay, so um, we can add it here anyway. So add live prediction candles to around, I think, 100 perhaps. Okay, now follow mode, whether we want a follow mode or not, use a follower that will look for models associated with a specific identifier and load those for inferencing. A follower will not train new models. All right, so it is like a follow mode where you have a system here, and you have a fleet of bots, fleet of machines, which will basically, you know, exchange parameters, update parameters in both ways. Okay, learning and updating the parameters. All right, so this will be our follow admin, if you will. And this will be our users, okay, which is followers, right? So yeah, I think let's just set it. Okay, let's just set it, follow mode is true. Okay, now we have continual learning. What it says is that use the final state of the most recently trained model as a starting point for the new model, allowing for incremental learning. More information can be found here, right? So yeah, we do want that, where we want continual learning. Continual learning, set to true. All right, now we have feature parameters here. Feature parameters. What we see here is that a dictionary containing the parameters used to engineer the feature set. Details and examples are shown there. So this is our feature parameters, this much. dictionary, right? So what we have here is include time frames, which time frames we want to add. Here we are adding 3 minutes, 15 minutes, 1 hours. We can use, we can add correlation data pair list here. We can add label period candles, right? We can use include shifted candles, which we are already seeing. We can add DI threshold, weight factor, principal component analysis, whether we want to use it or not. SVM, same case, whether we want to use use the SVM to remove outliers or not. And then indicator periods candles to populate RSI, ADX to period of 10 and 20, and then whether we want to plot our feature import. So that's all in the feature parameters. We can extend it to however we want as well. So that's a feature engineering part. Yeah, and these are the like include time frames that we consider, that we covered. Include time frames, a list of time frames that all indicators in populate any indicators will be created for. The list is added as features to the base indicator data set, right? Then we have include correlated pair list, a list of correlated coins that FreqAI will add as additional features to all pair whitelist coins. All indicators set in populate any indicators during feature engineering, right, will be created for each correlated coin. The correlated coin features are added to the base indicators data set. Okay, so every coin we have, either we have ADA, USDT, Alice, USDT, ETC, they all gonna use the same correlated pair list added to their data frame. All right, so that they have better feature representation there. All right, now we have label candle periods, label period candles here. This one, right, it says that it is a number of candles into the future that the labels are created for. This is used in populate any indicators. Okay, so for detailed uses you can create custom labels and choose whether to make use of this parameter or not. So let's go to the example there and let me show you what they mean by that basically. Right, so here in this strategy, FreqAI example strategy, here they're saying go to populate indicators, populate any indicators basically, and this is where we are using those label period candles to predict in the future, right? So there's the label period candles. And now let's look at the next. What we have here is include shifted candles. It says that it adds features from previous candles to subsequent candles with the intent of adding historical information. If used, FreqAI will duplicate and shift all features from the included shifted candles previous candles so that the information is available for the subsequent candle. Yeah, we already discussed it. All right, so we just want to give as much information as possible and useful information as possible to our model to train and learn from it. Okay, now we have weight factor. So here it's basically in this include shifted candles is saying that like we want our model to learn but what has happened for last 5 shifted candles and combining with current candles predict the next 5 or 10 candles. Like, is it gonna be uptrend, is it gonna be downtrend, or is it gonna be neutral, right? So that's what we are doing there. Okay, now with weight factor, what we're seeing is that weight training data points according to their recency. Okay, so it's just a linear algebra thing. And then we have indicator max period candles, which says like it is no longer used, so let's not look into it. Okay, now we have indicator period candles, which is this time periods to calculate indicators for. Okay, so we have indicator periods candles here. It's saying time periods to calculate indicators for the indicators are added to the base indicator data set. Okay, so a earlier we were using RSI, right? So we can calculate RSI for 10, previous 10 closing price and previous 20 closing price to get a better idea of for 10 it might be like it has crossed above, for 20 it might be like okay it's still going up. So if we are here, then yeah, we can go, we can like still go for long there. Okay, so that's information I want to think of it like as a, we are giving the model a chunk of information each time we are making progress. Okay, either in uptrend or either in downtrend basically. And that's what this shifted data and periods of candlestick smoothing of signal, it's what it is, this indicator for periods candles. Okay, which is very important by the way. Okay, we have all used like simple moving average, um, you know, closing price. If you look at it, is all, it's also a, you can like make, you can take the, well basically simple moving average is just the moving average of last 20 or 30 candles, and that's where this indicator periods candles comes from, and we can use as many as we want. Okay, so that's good. Then whether we want to use principal component analysis or not, right? And what it does is that PCA will automatically reduce the dimensionality of the data set using principal component analysis, right? So it's quite mathematical, where we use eigenvalues to basically, you know, see which features are important and only choose those features. Okay, which will lead us to this solution. Okay, there will be many features here, so whoever features are leading us to this convergence, that features will choose only, and whatever features is here and there we won't be using that. So we'll be using, like if we have 118 features, we can potentially reduce it to 50 features. So it gives us that computational, you know, advantage. Okay, now we have our feature importance, which basically create a feature importance plot for each model. For top, bottom, plot feature importance is number of features. Okay, so it will basically import, I mean plot a feature importance. Okay, so I think it's a good idea to analyze the trade and I mean features as well, and let's just add it. Okay, also use principal component analysis. If okay, let's just see, play with it. Okay, and how it works, then we'll see like we can, you know, modify it to our use cases. Okay, now we covered our plot feature importance. Now we are into DI threshold, which activates the use of dissimilarity index for outlier detection when set to greater than 0. Okay, so it basically like it's saying that data type typically less than 1 positive float. Here we have set it to 0.9, meaning if the prediction are greater than 0.9, then it will discard that, or greater than even 1, it will discard that. Okay, threshold basically. Okay, now we have use SVM to remove outliers. Here we are saying train a support vector machine to detect and remove outliers from the training data set as well as from incoming data points. See details about how it works. Okay, so what it's saying is that we can train our support vector machine to remove outliers from our training data set, which I already explained in the previous video. So check that out if you would like to see it, you know, live. Okay, now we have SVM parameters. You can also give some SVM parameters here. So we are using SVM remove outliers. Okay, so we can pass SVM parameters saying all parameters available in sklearns SGD1 class SVM. See details about some selected parameters here. Okay, so right now we can add it and then change it later. So svm param, and just let it this. Okay, then we can say here add optimized svm parameters. Now svm is done. Now whether we want to use db scan to remove outliers, so cluster data using db scan algorithm to identify and remove outliers from the training and prediction data. Okay, so it's same as like using svm or db scan. Okay, so we are using svm here, so that's good. Okay, now inlier metric window. If set FreqAI adds an inlier metric to the training feature set and set the loop back to the inlier metric window, that is the number of previous time points to compare the current candle to. Details of how the inlier metric is computed can be found here. Okay, so do we have a inlier metric? Okay, I think it's a bit advanced, which is, I suppose it's in the next section, which is feature engineering. I think, yeah, feature engineering. Okay, so we're gonna look it into feature engineering, which is quite mathematical though. Okay, now we have noise standard deviation. If set the FreqAI adds noise to the training features with the aim of preventing overfitting. Okay, now FreqAI generates random deviations from a like Gaussian distribution with a standard deviation of noise standard deviation and adds them to all data points. Noise standard deviation should be kept relative to the normalized space, that is between -1 and 1. In other words, since data in FreqAI is always normalized to be between -1 and 1, noise standard deviation is like 0.05 would result in 32% of the data being randomly increased or decreased by more than 2.5%. That is the percent of data falling within the first standard deviation. I think we had talked about it right in the previous video. So yeah, okay, but it is, I think, in order to prevent our overfitting, it is important though. So let's add it here. Okay, so let's add it. What we have here is an noise standard deviation. Let's just set it to 0.05, so that we want our 30% of the training data being randomly increased or decreased, because we don't want to overfit our model. Okay, overfitting meaning it would remember every aspect of sorry, like where it has shown like up move or down move, and it would basically like mess up with the system performance. So we do wanna let this machine learning system learn on its own. Okay, so now we have outlier protection percentage, which enables us to prevent outlier detection methods from discarding too much data. If more than outlier protection percentage of points are detected as outliers by the svm or db scan, FreqAI will log a warning message and ignore outlier detection. That is, the original data set will be kept intact. If the outlier protection is triggered, no predictions will be made based on the training data set. Okay, so I think it's very important, and let's add it to here. Reverse, what is it, outlier, right? Outlier protection percentage, we want it to be like 50%. At least we want 50% of the data. Okay, training set. Now if it is more than that, then don't throw the data away. Okay, so we have reverse train test order here, which says that split the feature data set and use the latest data split for training and test on historical split of the data. This allows the model to be trained up to the most recent data point while avoiding overfitting. However, you should be careful to understand the unorthodox nature of this parameter before employing it. Okay, reverse train test order, which splits the feature data set and use the latest data split for training and test on historical split of the data. This allows the model to be trained up to the most recent data point while avoiding overfitting. However, you should be careful to understand the unorthodox nature of this parameter before employing it. Okay, so right now let's just enable it as just we want, for the sake of the completion, we want it to be set as false right now, but we can set it later. Now yeah, now what we have is write matrices to disk, which collect train timings, inference timings, and CPU uses in JSON file. Okay, yeah, I think it's good to collect data, so let's get there as well. So we want a write matrix to disk. I feel like I have to, like, move this to below, but in feature, I mean about data split parameters here, let's see where it leads us to. Okay, then we have data split parameters. Okay, we have data split parameters, which says it include any additional parameters available from scikit-learn test train split, which are shown here, external website. Okay, yeah, so it includes any additional parameters available from sklearn scikit-learn test split. Okay, so we have test size here, random state. Okay, so we are testing on 33% of the data and training on 67% of the data. Okay, here we have test size, the fraction of the data that should be used for testing instead of training. That's it. That's the test size, 33%. Shuffle the training data points during training. Typically not remove the chronological order of the data in time series forecasting. This is set to false. Yes, we don't want to set this to true, because we are dealing with time series data in financial market, and it must be not set as shuffle. Okay, so yeah, now let's look at the next. What we have here is model training parameters. So a flexible dictionary that includes all parameters available by the selected model library. For example, if you use light GBM regressor, this dictionary can contain any parameter available by the light GBM regressor. Okay, if you select a different model, this dictionary can contain any parameter from that model. A list of the currently available models can be found here. Okay, so as earlier we look at like cat boost, XGBoost. So what we can do, we can go to their like official site and take out which are whatever parameters they have, and we can add it to here. In the case of XGBoost, CatBoost, the most important parameter they have is the n estimators, the number of decision trees, basically number of decision trees we want in our model. That's our n estimators. Okay, so yeah, so think of it like you give this model data point, it has some tree over here. See this, this can branch out to anything. Okay, now here it's making some decision with that candlestick, with that RSI. Here is gonna go and make some like relationship with ADX. How does it work? Here is gonna go to simple moving average, and then you have all this collection of n estimators, right, with decision trees, and then you finally get this output of like either regressor output or classifier. Okay, so that's the goal here, or multi-class classifier basically. So that's how it like finds the relationship between all those, you know, feature or indicators. And that's exactly what as we human do also, right? We learn all these indicators. Okay, moving average, if like 30 crosses 50, then go long, you know, see if there's a resistance line there, a trend line is there, whether the RSI crossed above 30 or not. So yeah, it like that's exactly what the machines are doing, but they are doing in a much more efficient way. Okay, so we have our n estimators. Now we have learning rate, which is a boosting learning rate during training of the model. Okay, which is by default is good. Okay, now we have n jobs, thread count, and task type, so which is the set the number of threads for parallel processing, and the task type, a GPU or CPU. Okay, different model libraries use different parameter names, so I can go ahead there and add it, right? So I can go ahead and say you know what, I think it's around here. So n jobs would be, let's put -1. I mean, use all the processors we have, and that thread count can be around 8 thread. I want to run 8 thread at the moment, and then the task type I want to use GPU, okay, or CPU in this case, and let's decrease the thread to 4, I think, right? So yeah, so we done that. And then Keras is, if the selected model you makes use of Keras typical of for TensorFlow based prediction models, this flag needs to be activated so that the model save or loading follows the Keras standard. So in the future we're going to be building a transformer model, all right, transformer architecture based model. And if you follow deep learning area, I think you might also have heard about, you know, diffusion model and all. All right, so basically it's based on transformer architecture, and we can use the same architecture for training any data we want. Okay, same architecture for any input data. All right, so whether it can be structured and unstructured, in our case we are dealing with structured data, as well as some of unstructured data, in a sense that model needs to find out some patterns in it. Okay, now we have our other parameters here, convolution width, which is the width of a convolutional neural network input tensor. This replaces the need for shifting candles, includes shifted candles by feeding us in historical data points as the second dimension of the tensor. Technically this parameter can also be used for regressors, but it only adds computational overhead and does not change the model or training prediction. So it's good to have, but as I said, in the future we'll be looking at the transformer architecture, and so you know, we will be using this convolutional neural networks as well for building our architecture. So let me just add it here, Keras false. Okay, and yeah, right. So I think that's it for this video. Please like and subscribe, and let me know what you guys think in the comments below, and I'll see you guys in the next video. Thank you.